So today I'm going to talk about a virtual metrology project, which I've been working on, and it looks at both sort of a framework for thinking about virtual metrology systems and also ways to model them. So I'm going to start off by giving a overview of the problem and sort of the motivation of this project. And then after that, the project's going to be, or the presentation is going to be split into two different parts. The first one is going to be talking about this framework for virtual metrology systems that I have been thinking about. And the second half will look at ways to model both that framework and virtual metrology systems in general. So I'll first by introducing the framework and then talk about the sources of error that come from all modeling given this framework. And then I'll talk a little bit about how you could figure out which of these sources of error you're suffering from in real systems. And then for the modeling itself, I'll mostly be looking at Kalman filters, which are a probabilistic way of modeling unobservable variables. In this case, we're going to be looking at the relationship between sensor and what we're trying to measure, or sensor variables and the output variables that we're trying to model. And we're going to use Kalman filter to model that relationship. The main thing which I'm going to compare to is a weighted OLS model, and I'll talk about that a little bit. And I'll look at the impact of changing both the system conditions and some other things, and looking at the impact on the performance of both.
Chris, before you go, can I just ask you why you aren't considering HMMs?
So
reasonable comparison method.
I probably should. At least in this framework, the underlying system is a linear system. So
okay, that makes sense then.
Yeah. But I do think that that would also be another good method to look at. At the end, I'm going to talk a little bit about comparing them to neural networks for nonlinear systems, but that's more of a future work or / current work thing.
Yeah, sure. Okay.
But I should also think about hidden Markov models as well.
Okay, thanks.
So the goal of virtual metrology is to create a representation of some product or key properties of it without needing to take explicit measurements. And it's mostly used in this term is mostly used in the semiconductor industry, although there's probably analogies to it in other industries. So for us, we may want to model things like thicknesses or geometric variations of our devices, or things like the doping concentration of those devices. But for other applications, I could see you wanting to create a virtual model for things like the pH of a system or some other purity or geometric variations. And the key to this is that we don't want to take explicit measurements of these things, which may be very difficult or invasive or expensive to measure. We want to be able to come up with a model that uses some sensor information inside of the tool to estimate what these key properties are. So sort of the high level goal of this is both to come up with some framework to create a digital twin or a virtual model for the outputs of interest based on these sensor inputs. But also another key aspect of this project in particular was to try to think a little bit about the sources of error that you would have for a given system. So I ended up coming up with this framework for virtual metrology systems, which I think ends up capturing sort of the main ideas and what is going on. And it can describe, I think, most different virtual metrology systems. And I end up using this framework to both develop modeling techniques, compare different ones, and also help me think about the sources of error that arise from this framework. So here, there's 4 main variables of interest. There's the recipe, which is the input to the system. And this could be something like targets for the product that you're looking at. And then there are chamber variables, which we don't directly observe, but they impact both the sensor values that we end up observing and also the wafer in the semiconductor application, the wafer variables that we are trying to model. So we don't know what these chamber variables or how many of them there are, but we do know that they end up impacting both the sensor and the wafer itself, or the outputs that we're trying to model themselves. So here, the recipe variables are related to the chamber variables through some unknown function, and also the chamber variables are related to the sensor and the wafer variables through their own unknown function. So if you set the recipe for something, that's going to change the state of the chamber, and then the state of the chamber is going to impact both the sensors that we're recording, and also the final product that we're trying to model. Initially, I am assuming that all of these systems are linear systems, and this is an assumption that I'm going to revisit a little bit later. But at least to start off, I'm thinking about each of these systems as linear. So here, the chamber variables are AC times the recipe variables, and then the sensor variables are AS times the chamber variables, and the wafer variables are AW times the chamber variables. So the second key aspect of this system framework is the fact that these relationships aren't constant over time and that they tend to drift over time. So this makes sense because we think that the state of the chamber is going to be drifting over time. So this AC variable is going to be changing. And also the relationship between the chamber and what we're observing, both the sensor and the wafer variables, are also going to be changing over time. So to add this to this total system framework, I end up modeling the coefficients in these three systems, AC, AW, and this should be AS and AW, as bounded Gaussian random walks. And a normal Gaussian random walk, you end up just adding a small amount of Gaussian noise to it at each time step. But the problem with this is that if you let this go for a long period of time, its value is going to explode. So we end up scaling it by some coefficient in order to keep the bounds in order to keep the amplitude or the expected value of variance constant over time. So with this framework in mind, we can think a little bit about the system itself that we're trying to model. What we're trying to do is predict these wafer variables as a function of our observed sensor variables. So if we know that the wafer variables are AW times the chamber variables, and we know that AS is the chamber variables times the sensor variables, we can say that the chamber variables are AS inverse times S, and then we can rewrite the wafer variables as AW AS inverse times S. So this means that we actually don't care about what the relationship between the recipe and the chamber is. We only care about the relationship between the chamber and the sensor, and the chamber and the wafer. So with this in mind, this system that we're trying to model or keep track of, AW times AS inverse, sort of implies two different sources of error. The first is a little bit more intuitive. Because these systems are drifting over time and they're changing from time point to time point, this system that we're trying to model is also changing over time. So we're going to have some error in our modeling just due to the drift of this system that we're trying to model. However, if most of the drift is occurring in AC, so most of really what's changing is the state of the chamber itself, that means that the system that we're trying to model is actually constant. So that's easy to deal with because what we're trying to keep track of, AW times AS inverse, this is actually constant in time, and we can deal with changing systems in the chamber as long as we can still infer the wafer values from the sensor variables. The inverse of that is that if drift is occurring in the relationship between the chamber and the sensor and the chamber and the wafers, that's actually more difficult to keep track of. And I think that this is a little bit less common, so it makes sense that the chamber or the tool itself would be changing over time. Stuff could be accumulating on the inside of it. It could be getting worn down. But it's a little less likely for there to be drift in the relationship between the chamber and the sensor, or the chamber and the wafer. So what this would mean is, let's say the chamber temperature ends up going up. Over time, your sensor would not be picking that change, would not be measuring that change in the same way that it was before. So that changes in AS and AW, I think, are a little bit less likely than changes in AC or the chamber itself.
Chris, can I ask you about that?
Yeah.
So it does seem, so I guess I'm wondering where like measurement noise comes in here. So you're talking
Okay.
about
Yeah.
drifting noise, but how do you measure measurement noise?
So there is also, I don't directly estimate it, but I do, when I simulate this, I do also add noise to both the wafer and the sensor values.
Okay.
So it's just like Gaussian added noise added on
Yeah.
top.
Okay.
But I didn't put that in here.
But so you wouldn't think of that as, yeah, it doesn't
Yeah.
make sense to think about that as the change in the relationship between the
Yeah.
sensor.
So yeah, I basically just added on as there's additional Gaussian noise added to both the sensor and the wafer.
Yeah. Okay.
The second source of error from this framework is a little bit less intuitive than the drift in the system itself. I call it opaqueness error. There might be a better term for it. But what it means is that if AS is not fully invertible, then we actually can't figure out, even if we knew what AS was, what all the chamber variables are just from sensor measurements. So if AS is not invertible, for example, if there are more chamber variables that impact the sensor and the wafer than there are actual sensors, we can't get a clear vision of what's going on inside of the chamber. So that's why I call it an opaqueness error. And because we can't get a full idea of what's going on inside of the chamber, we can't then predict the final product that we're trying to predict. So the second large class of errors I call opaqueness errors. And we can look at the opaqueness error in a little bit more depth. So I sort of fudged things a little before when I said that we want to model AW times AS inverse. If AS can't be inverted, then this expression doesn't make any sense. But what we can do is use the pseudo inverse for AS instead to account for a non-invertible AS. And this is just the expression for a pseudo inverse. It's basically the most common inverse approximation for low rank systems. So when you can't fully invert the system, we have this approximation for what it could be. And then with this in mind, we can look at what we expect the error to be. And here, if the error is the difference between the real wafer values and our predicted wafer values, we can write this as the real wafer values, which are AW times the chamber variables, times the predicted ones, which is going to be AW AS pseudo inverse, times the sensor variables here, which are AS times C. And then we can factor out this identity matrix minus AS inverse times AS. And we arrive at this expression where our error is going to be AW times this term times the chamber variables. And for a specific set of chamber variables, we could compute what the error is. But another way of looking at it is what I call the error matrix. And that is just this first section here, AW times I minus AS pseudo inverse AS. And this says that each term in here is the error for a specific output variable I per amount of chamber variable J. So basically tells us for one of these specific systems how susceptible we are to opaqueness error. The downside of this is that it only works for a theoretical system that follows this framework and doesn't actually apply to real data. But in a little bit, I'll talk about how to estimate opacity error from real data. But it's still interesting to look at. And just sort of to give a simple example of this, if we have 5 chamber variables that impact 2 wafer outputs and 2 sensor outputs, we can imagine a situation where our sensor matrix looks something like this. So we have 2 different sensors corresponding to the 2 different rows. And let's just say that they're each measuring 1 different chamber variable, but the other 3 here are unsensed. Then in our wafer matrix, we have again, 2 different outputs. The first output is not significantly influenced by any of the chamber variables, but the first one is influenced by the first and the third. Here, our error matrix would say that we have 0 error from these first 2 chamber variables because we can perfectly infer them from this sensor setup. We have a large error from in the first output from the third chamber variable because we cannot sense it at all. And it also has a big impact on the output. And then for the other terms that we can't sense that may have a lower impact on the output, they have a relatively small contribution to the total error. So what this is meant to point out is that the opaqueness error is a combination of two different things. It's one, how well can we infer these different chamber variables? So for these, we can infer them very well so they don't contribute to the error. And also, we need to look at how impactful those chamber variables are to the wafer, because we can set an infinite number of chamber variables, theoretic ones that don't actually impact the final product. So we have to look at both how well we can infer them and how impactful they are to the properties that we're trying to measure or predict.
Chris, I would think that like the quality of or the validity of the linearity assumption would also affect the opaqueness error too.
Yeah, so that is sort of I don't really talk about it too much here, but I think that also the third big class of error is model model mismatch error. So if your model just doesn't match what the underlying system is, then you're going to have error as well from that.
So I guess my point is I would think that if you're in this simple example, you're assuming that you can you're assuming that your impact is linear, right?
Yes. Yeah.
And so you may get into a situation if you have a highly nonlinear impact, then you could be able to measure a chamber variable, and it might be important, but it might not be picked up because it's a nonlinear relationship, right? So that could impact your estimation of the opaqueness error, I guess is my point.
It could also impact your estimation of the opaqueness error, definitely.
Okay.
But I do think that those are two separate things.
Sure.
Because even we could have a nonlinear system where there are unobservable chamber variables that still impact the wafer.
Yeah, agreed.
So yeah, I didn't really talk too much about model mismatch error in this. That's sort of the thing that I'm looking at mostly right now.
Oh, okay.
And I have one slide at the end that talks a little bit about that, but I do agree that that is really the third big class of error that I would expect to see in these systems. So the second class of error that, the second one that I'm going to talk about here is error due to the drift in the underlying system. So because at each time step, these systems will drift in a random direction, even if we can fully infer these chamber variables. If we don't know, for example, what AW is, and we have perfect information of what the chamber variables are, we're still going to have some error in our predictions of the wafer or the final product. And I don't have quite as nice of a closed form analysis for this because things don't stay Gaussian. But there's a pretty easy way to empirically determine the drift error. Given one of these setups, we can simulate multiple instantiations of a single drift many times, fit a model to that, and then see what the error would be given the best model under the conditions of the drift. So that is a way that you, given this theoretical setup, can evaluate what percentage of the error will come just from drift itself versus from opacity. But like I said before, this is really only useful in determining the error for theoretical systems, and it's more useful to us if we can figure out what these errors are for real systems with real data. So we may want to be able to figure out how susceptible we are to either drift or opacity errors just from wafer and sensor measurements alone. And the one method for figuring this out is pretty simple. Again, it assumes that we have the correct model form, but we could build a model for the W as a function of S from just a small section in time, figure out its initial accuracy, how quickly the model drifts, and the final accuracy. And here, this initial accuracy will determine the opacity error. So if you have built a model just from, it's basically the training error. if our training error is very high, then we know either we have a poorly chosen model or it's impossible to solve because we have this opacity problem. And then how quickly the error changes and what its final error is tells us what the drift error is. And we can end up averaging this over many ensembles in order to reduce noise. So I did this with data that was simulated from that system, where I ended up fitting a model on one section in time, predicting future values, and then sweeping this training window across the training data set in order to get more of an averaged graph of prediction time in the future versus model error. And there's really two important parts of this, possibly three. The first is what your initial error is. That's basically your training error, and that corresponds to either how opaque your chamber is or how mismatched your model is. And then also we can look at the both decay constant of this fit. This is just an exponential decay, and also what its final value is in order to give us a sense of how quickly the system is drifting and how bad it will perform if we let it drift forever. So I ended up generating that data and sweeping both the drift rate of the underlying system, so how quickly these systems are changing over time, and also the number of different chamber variables. And here I have 10 different sensors. So if we have 10 or fewer chamber variables, we should expect that we can essentially perfectly invert AS, and we have a clear vision into the chamber, and we should have very little opacity error. So this bottom graph shows that when we have fewer than 10 chamber variables, we essentially get perfect perfect training fits, which means that any error is not going to be due to opacity problems. But then once we start including more chamber variables, opacity error does get introduced into our model. And similarly, when we sweep the drift rate of the system, the number of chamber variables does not have a huge impact. But when we end up increasing, or sorry, when we look at the time constants of the system, so the time constant of this decay here, the number of chamber variables does not really impact that, but it does impact, but it is impacted by how quickly the underlying system is changing, if that makes sense. So this isn't the most sophisticated method, but it does give us a pretty good idea of how susceptible a specific system is to either drift or opacity, or potentially also modeling error just from wafer and sensor measurements. So in the first half, I was mostly talking about the framework for this itself, and I didn't really talk about how I would end up modeling this system. So for the rest of the time, I'm gonna talk about the way that I would think about modeling this system. So if I actually wanted to build a model for W as a function of S, and I end up, again, using this framework when I'm evaluating the proposed method and also different methods. So in general, what we want to do is at each iteration, drift the underlying system a little bit, collect sensor data, make a prediction on what we think W as a function of S is, compare it to the true value of W, and then update our model. So just a quick reminder, the system that we're trying to model here is AW times AS inverse. And what I ended up doing was treating A as an unknown multivariate Gaussian random variable, and then updating the belief of A as new sensor and wafer pairs come in. And then at each time when we think the system is drifting, decaying or drifting the belief of A at each time step. And it turns out that I'll go into this a little bit more in depth, but this approach of modeling the underlying system as a Gaussian random variable, a multivariate Gaussian random variable, is actually the same thing as a Kalman filter. And so I ended up sort of reinventing the wheel a little bit. Kalman filters are normally used to estimate some unobserved value as a normal random variable in real time. And what they are most often used for are modeling things like the position of something. So guidance and navigation is sort of the traditional use of Kalman filters, but they're also used to model things like electrical grids, robotics, vision systems, basically any variable that you want to track over time and can be inferred from some observations. So when we end up getting new observations, we can update our belief of this unknown or of this unobserved or unknown variable. So you can imagine that if we want to model the position of a car, which let's say is our unknown variable of interest, we have some prior state belief. And then let's say that we get a new measurement. It could be a velocity measurement that would assume that the car should be in this position here. We would then update our belief given this new measurement, and we'd arrive somewhere in the center of it. However, here, what we're not modeling a single variable of interest. What we're trying to do is model this input-output relationship of the system A, and that's actually our unobservable variable. So it's a little bit different than what you would normally end up modeling, which is a single variable like the position or the pH of a system. We're trying to model this input-output relationship. So it's a little bit different. Also, just a note, you could end up using this to track any input-output relationship. It's not specific to this setup here. So with in the Kalman filter framework, you end up having two different steps. You have this evolution step where at each time point, we expect our state or what we're trying to model to change a little bit. So it's going to be both a function of its previous state, some inputs to the system, which in our case are unused, and also some random noise. In this case, this random noise represents our bounded random walk. And then the second part of this modeling is the observation step. So here we get some new observations, which are a function of our hidden state, but are not necessarily direct observations of our hidden state. And then we also, again, have some observation noise on top of this. So I'm not going to go too deep into the math, but when the observation or the update when we get new observations is one half of it. And here what we want to do is come up with some probability for what our new A matrix should be given some input X and output Y. And here X should really be the sensor variables and Y should be the wafer variables that we're trying to predict. And we can rewrite this as the probability of seeing these wafer variables given the sensor variables and our value A times our prior belief of what A is. So if we can rewrite this essentially into a new Gaussian random variable with a new mean and a new covariance matrix. So the math getting from here to here doesn't matter too much, but essentially when we get new sensor wafer pairs or new sensor wafer pairs, we can update our belief of what we think the relationship between the two of those is. So when we end up, that tells us how to update our model when we get new information, but we also know that this model or that this relationship, AWAS inverse, is also drifting or changing over time. And we also need to incorporate that in this evolution step here. And I made a little bit of a mistake when I was first going through this. I originally thought that since AS and AW were following a Gaussian random walk, the system that we're trying to model, AS inverse AW, would also follow a Gaussian random walk. And what this would mean is that at each time point, our system would essentially just have a small bit of added noise to it. And we could update our belief just by adding an additional covariance matrix to our existing covariance matrix. And if this was true, this would give us the optimal closed form solution to tracking this relationship between the sensor and the wafer variables. However, I realized that this was not the case. And given that assumption, I assumed that the Kalman filter should have been optimal with that formulation. But I ended up testing it against weighted OLS, which is just normal OLS, except we end up weighting more recent points in time more than points very far in the past because they're more relevant, and just using an exponential decay for this. And when I ended up testing it on data that I synthesized from the system, it actually outperformed the Kalman filter, which was a little bit surprising. And I ended up scratching my head for a little bit. And because I was pretty sure that the Kalman filter should have been optimal and I should not have been able to come up with a better model for that. So it turns out that the assumption that I made that was wrong was that the drift of the system that we're trying to model is actually does not follow a Gaussian random walk. So we can figure out, because we know what AS and AW are, we can figure out what the optimal underlying system is. And if we look at one of these coefficients over time, we see these really large spikes in it. And this definitely does not look like a random walk or a bounded random walk. And there's two problems with my assumption. One is that the product of two Gaussians is not a Gaussian. So if AS inverse was Gaussian and AW inverse was Gaussian, the product of these two random variables would not be a new Gaussian random variable. I sort of knew this, but it's sort of a second order effect, and I didn't think that it would be very important. But what is more important is when we end up taking the inverse of AS inverse, we no longer, when we end up taking this inverse, that really destroys the assumption of a Gaussian random walk. And in particular, when the eigenvalues of this matrix that we're trying to model end up crossing zero, that's when we see these really large spikes in what the optimal system should be. And so you can imagine that if AS was following the path of a potential Gaussian random walk that was -2, -1, 0, 1, 2, when we end up doing the inverse of that, it blows up at 0. And so that's why we tend to see these really large negative spikes followed by really large positive spikes. So it's when the eigenvalues of this system cross 0 that we actually run in, that our assumption of a Gaussian random walk no longer holds. However, we can add another assumption to this, which actually makes this a realistic assumption, in my opinion, which actually makes the previous approximation pretty good. So if we end up saying that these coefficients that we're trying to model have non-zero means, then the relationship between, then AS inverse actually does follow a Gaussian random walk, and the combined system as well approximately does as well. So you can factor out AS and also AW as some mean value plus some deviation from the mean value. And then you can take the inverse of this and show that you can approximate it as essentially a Gaussian random walk. And then when you take the product of these two, you can say that you have some mean value plus some Gaussian random walk value plus another, and then plus this second order effect, which you can mostly ignore. So it's not really worth going too deep into the math, but sort of the punchline is that if these coefficients in AW and AS have non-zero means, in particular if AS has non-zero means, then this whole system does follow the assumption that we were making before.
Can you talk about that assumption? Oh, okay. You're going to talk about it.
Yeah. Okay. Well, this is mostly just a demonstration of it. So
okay.
Here what I did was I said, let's initialize the system again, but let's have, instead of the coefficients in AS, AC, and AW be a zero mean bounded random walk, if we just shift these values up and have them have a mean around 3, for example, or some coefficient times the standard deviation, then we would assume that the underlying system follows the approximation that we were making for it, and the Kalman filter should be optimal. And in this case, I just compared WOLS to the Kalman filter, sweeping the mean value over the standard deviation of it, of the individual coefficients in A. And the only case where the WOLS outperforms it is when the mean of these coefficients is 0 and our assumption is broken. And in all other cases, the Kalman filter outperforms it and is the approximately optimal system. But did you want me to talk a little bit about?
Yeah, so my question was about like what this assumption means.
Mm-hmm. So let's say that really it's most important in AS. AW, I think, can have 0 means and it will still be fine. But let's say that the chamber, one of the important chamber variables is temperature, and we have a sensor that's measuring temperature. It will do, the Kalman filter will track this relationship pretty well as long as the relationship between the chamber temperature and what we're reading floats around some value and does not go from saying if the, and
yeah,
doesn't cross 0.
Yeah, basically the correlation between what you're seeing and the unobserved variable doesn't flip signs.
Yeah, as long as that, as long as it hovers around some value and doesn't end up crossing 0, then it's a good approximation. And
okay, yeah,
and it does make sense because like and I think it's a realistic assumption because we wouldn't expect our temperature sensors to start reading negative values if just due to like random drift of the underlying system.
Yeah.
So does that mean the measured sensor value needs to be positive, not the drift comparing the measured value to the actual temperature?
Sorry, can you repeat that?
I just clarifying what you meant by that it can't go negative. So you're meaning like the actual measured value from the sensor can't be negative, or it needs to stay on one side.
Yeah, it's a little subtle, but the relationship, anything can be negative, but you generally don't want the relationship between the sensor values and the chamber values to flip sign.
Gotcha.
So let's just say that you can have negative temperatures, we're in Celsius or something. If we have a sensor that is measuring the temperature inside of the chamber, it can say that these sensor values can be negative and the chamber values can be negative. Also, it could be fine that our sensor values are giving us the negative, the actual chamber temperatures. But what does cause a problem is if the relationship between these chamber variables and the sensor variables changes sign. So let's say that the chamber temperature is 1 and the sensor red temperature is -1. And that would mean that AS starts at -1, but if that drifts to +1, then all of the sudden, then at that 0 crossing, or in general, AS would have drifted from -1 to 1. If our chamber temperature stays at 1 and our sensor temperature drifts from -1 to 1.
So is it important to have the data in engineering units like that? Where you measure, you have temperature as a temperature? I'm thinking like
if there's just a mean offset.
Sorry?
If there's just like a mean offset to something.
Or like instead of like you're saying it's 25 degrees Fahrenheit, it is 10% of span, because then you could clamp it between 0 and 1 and not have any.
Yeah. That's something which like has sort of been in the back of my head, but I don't really have a good answer for. So like, if you just add some offset to all of these, does that fix your problem? Is that sort of what you're saying?
Yeah, because like if the sensors, or I mean, not that it really matters the way they communicate, but it's a scale value, right? You're getting something between the minimum measurable and the maximum measurable, which you can put that in any spot you want. Just didn't know if that actual relation, like that physical relationship and units, or like numbers of the correct unit and dimension matter.
I don't, honestly, I don't have a good answer for you. I sort of have, my gut feeling is that it shouldn't matter, especially to scaling issues. Offset, I'm not 100% sure on. So I need to think a little bit more about that. I don't have a good answer to that at the moment.
So Chris, I think it does make, it is a reasonable assumption, I think, that this relationship shouldn't change signs, but why couldn't it hover around 0? Like, why couldn't you have entries of A, S that are 0?
So let's say that AS is just flipping between -1 and 1 at each time step.
Yeah.
If we try to, or let's say like at each time step, it just randomly chooses -1 or 1 to be the value of AS. Then we don't know if the sensor values that we're reading are actually giving us.
No, I get that, but why, like, maybe there's something else I'm missing, but why couldn't a element of AS just be 0?
Yeah, so that is another question which I really don't have a complete answer for. I feel like it should be able to be 0. Because it's not the elements of AS that have to be 0, it's when the eigenvalues cross 0 that there's a problem.
Right, okay.
Yeah, so you can still have elements that are 0 and the eigenvalues are still either positive or negative. But it's easiest for me to think of these as a single number and not a matrix.
Yeah. Okay, that's what I missed. Thanks.
A question about the kind of the temporal relationship. So for effects that you may sense at one point in time, but don't really become apparent, say like in the wafer until later, and that might be modified or attenuated by different effects that are measured at different time points. Does that affect this at all?
Are you saying that like there's something that we sense at time t=1 that doesn't actually impact the product until t=10?
Yes, and somewhere between 1 and 10, if something else changes, that changes the impact from like from time = 5 to 10. Like if you had like changing a flow and then halfway through changing a temperature, you're gonna have a different amount of heat delivered.
So if two different things end up canceling each other out?
Not so much canceling out, but like, so like if you had like a constant flow at one point, or like a ramping flow, and then you add heat to it halfway through, then at the end you're going to have a different amount of heat delivered than if you have that constant amount of heat from time = 0. So just like how there's a time lag between reading something and when the effect is like
yeah, that's I see what you're saying.
I feel like we're talking about model mismatch error again, don't you think?
That sort of does tie into model. I can see that tying into model mismatch error. Like, I guess in this, definitely not in this framework, there's like no way for things at time t=1 to impact things at time t=5. But that's actually something which I hadn't thought about and is, again, something worth considering.
Well, but you could just say
add additional inputs to the system.
Yeah, right. Yeah, you could add lagged sensor measurements, right? As a sensor measurement.
Yeah, so, I guess I was thinking just in terms of things that don't have a linear relationship on each other that you can't just account for it by time lagging one thing back, or maybe even a combination of things. But I don't know how relevant that is for like this process. Maybe everything is very nicely linearly related.
That's an assumption that I'm making.
Maybe.
So I'll get to the nonlinear stuff a little bit. Like that's something which I'm only just thinking about now. or like that I'm currently thinking about. To tie this up a little bit, it bothered me that even when we had zero mean processes, which is when we're most likely to get eigenvalues that cross zero, that the WOLS model performed better than the Kalman filter. And I felt like that shouldn't be the case. And there should be some way to sort of approximate or mimic a WOLS model using this Kalman filter. And you can do that by changing your decay function that models the random walk of the system a little bit differently. So instead of adding some small amount of noise to our covariance matrix, we can scale it by some amount. So saying that there's just proportionally more uncertainty in our system. And if we do that, if we use this update function for the model drift as opposed to a Gaussian random walk, we get the same results as the WOLS model. So at this point, I realized that I basically want both the drift in the covariance matrix and the scaling of it to perform well in either scenario. So I ended up using this combined update for our covariance or our uncertainty matrix for the underlying system, where we add some amount of constant drift to it, and we also scale it by some other amount. And so this means that we are both approximately optimal when we have non-zero means, and also when we do have zero means, we still perform pretty well and still better than WOLS. So I think that this is a pretty good solution to modeling the drift or the decay of the system, even though we don't have a good, perfect closed form optimal solution to it. Also, one interesting thing to look at is just how the drift rate of the underlying system and the number of chamber variables impact the performance of it. And this is pretty similar to what I showed before, which was the sort of theoretical opacity and drift errors, where again, increasing the drift rate ends up hurting the performance of the both the Kalman filter and WOLS, but still the Kalman filter performs better than WOLS regardless of how you choose the drift rate. And similarly, when we end up sweeping the number of chamber variables, or increasing the number of chamber variables, we have less of an idea of what's happening inside of the chamber. So the error for everything goes up, but again, the Kalman filter still ends up outperforming WOLS as a baseline comparison method.
Sorry if I missed this, Chris. This is a simple question. Where do you get the weights in WOLS? Are those learned?
Yeah, so it's, I'll just go back to that quickly. It's basically just normal OLS, except you end up placing more weight on more recent samples as opposed to older, less relevant samples.
Oh, you're assuming an exponential.
I am assuming an exponential.
Okay, so they're not learned. Okay.
Oh, sorry, they are not learned. You're correct about that.
Okay.
Although that is also another interesting aspect which I had not thought about. So a lot of good ideas.
Oh, okay.
But I choose the hyperparameter of this decay is something which I optimize for.
Sure, just like cross-validate for.
Yeah.
Right? Yeah. Okay.
But that's a good idea to actually try to learn the optimal weights.
Because then you might end up learning that decay.
Yeah.
Decay rate, right?
That is a really good idea. So I think I think it might not be a single. I think it sort of may depend a little bit on the position of the system, because when that Gaussian random walk approximation is valid, what you really want to do is just add some amount of drift at each time step. And I don't think that you can replicate that by just scaling the covariance matrix with a constant that is constant like at all points in time. And when you end up just using the scaling, it is equivalent to WOLS. So WOLS, no matter how you choose the scaling matrix, won't be able to replicate the addition of added noise, which is optimal in some situations.
Right. That makes sense.
But I still think it's a good idea to try to learn what the optimal scaling is.
Yeah, I mean, I imagine that someone's done that.
I imagine so as well.
So.
So the thing that I'm currently working on, which is something that has been pointed out before, is that a pretty big assumption that I'm making is that the underlying system is linear. And I think that for systems where we have a continuous function with a relatively small amount of drift at each time point, it's a pretty reasonable assumption. Because if we say that, for example, Fs is going to be some value of c plus some delta c, we can factorize this if it's a continuous function or smooth function as Fs of c plus some delta s times delta c. And this delta s here is essentially what our AS system that we're trying to model here is. So if it's only slowly drifting, our modeled systems, we can approximate them as linear around this operating point. And this relationship here may be changing over time depending on which operating point we've chosen. But hopefully we would hope that our model can keep track of that change over time.
That could break though with what Christian was saying, right? Like if you have variables that, even if your system's changing slowly, if you have variables that impact your current state from quite a few time steps ago, then you might not have a linear relationship anymore.
Yeah. I need to think about that a little bit more. So like you could still have variables from 10 time steps ago that have a linear relationship to your current state in time. I'm not 100% sure.
I guess what I'm saying is that so you could, I guess I'm saying that the risk of a nonlinear relationship increases substantially if you have long time lags.
Yeah. And it is a little bit strange to think about like what the definition of this operating point means when you start, because it's not just one point in, like the system is not one point in time when you have time lags as well.
Yeah, that's true. That's fair.
So,
okay.
Well, that doesn't really answer your question, but it is, again, something else for me to think about.
Yeah, right. I didn't expect you to have an answer to that. But.
So I think that even if the underlying system is nonlinear, I think that there's still a pretty good chance that a Kalman filter would outperform something like a dense neural net. So what I'm doing right now is, instead of saying that these are linear systems, I'm saying that there are some high order polynomial systems where we have the first order AS term times chamber variable plus second one times c squared to some high order polynomial. So the underlying systems themselves are polynomial functions, like not linear polynomial functions. And the reason that I'm doing this is they're nonlinear systems, but they still allow me to drift the model easily by just changing the coefficients in here. So it still sort of works in the same general framework. But it lets me see how the Kalman filter would perform against something like a neural network in these nonlinear cases. So it's something which I am still working on now, mostly just training these neural networks over doing hyperparameter sweeps for them, and also retraining them at many time points is pretty computationally intensive. So that's sort of what's slowing me down now. But I think that in a regime where we have very slow drift and a lot of transparency, so there's a constant system that that doesn't change over time, and we can get all of the information that we need from the sensors to predict the wafer variables, I would expect something like a dense neural network to be basically optimal and give us the best solution to predicting W as a function of S. But I also think that in a case where these underlying systems are drifting really quickly, and there could also be some added opacity, that is more prone to the neural net overfitting. So I think in these cases, I'm not 100% sure, but I sort of suspect that like a well-fit Kalman filter might outperform a dense neural network in these cases. However, this is something which I'm still working on and don't have results for at the moment.
Just what's the kind of like how many sensor values or sensors is this comprised of?
So in all of these experiments, I use 10 sensors and just one output variable. It also works like with many output variables, and I know that in practice, this isn't like for a specific process, but it was sort of the underlying process which led to this has 40 or 50 sensor variables and only one output of interest. So these results have 10 sensor variables, one output. A realistic use case would be somewhere between 0 and 50 or 0 and 0.
But I wonder, like, between those 0 and 50, how many are like really independent?
Yeah, that is another good question as well. Let me think. So when there are fewer chamber variables than sensor variables, you definitely have linearly dependent sensor variables. So if like you only have one chamber variable and 5 sensors, these 5 sensors are definitely dependent on each other, right?
I guess maybe mathematically, but process-wise.
Well, if there's only one factor that's driving the variation in your 5 sensors, then your 5 sensors must be.
If it is just one factor. I guess I was thinking if it's more than one, but you're just not including it.
I was mostly just saying you could easily have dependent sensors. You will have dependent sensors if you have fewer chamber variables than sensor variables. And that's something that I looked at in the past on one of the previous slides. And it basically does as well in that case as having as having a one-to-one relationship. But again, it's something for me to think about. So sort of to summarize all of this, virtual metrology is a really useful tool for making inexpensive estimates of a product quality aided by secondary sensors in a system. And I came up with this framework that looks at that uses this framework to identify 2 main sources of modeling error: opacity error, where you don't have full information about what's going on inside of the system, and drift error, changes in the system over time. Also, I didn't talk about it here, but I think the model, or we did end up talking about it, but I think the model mismatch is also probably a third really big category of error that you can have. And it is also worth considering. You could sort of lump that. It is distinct from opacity error. Actually, I take that back. It's definitely distinct from opacity error. Under this framework, I think that Kalman filters are a natural and often optimal way of modeling the relationship between the sensor and wafer variables. And I think it's sort of a particularly interesting use of a Kalman filter because normally they're just used to track a single value, but what we're actually tracking is this input-output relationship, which is sort of a little bit unique, I think. And even when you have the correct form of the model, a linear system, it ends up outperforming a traditional method like WOLS in a variety of different regimes for different drift rates, opacities, and means of the underlying coefficients. And right now, currently, I'm working on comparing this method to dense neural networks in nonlinear scenarios. So, comments, questions, thoughts?